Good morning to all my dear students. Welcome again in the continuing part of the chemistry of the hydrocarbons in the petroleum in Unit 1 of your paper Refining Process for the Crude Oil MSCH 305. We have read in the part 1 the chemistry of the paraffins and the olefins. Now we discuss the chemistry of the aromatic hydrocarbons, the naphthalene and the naphthalenes, which found in the crude oil in this lecture. The brief outline of my presentation, the review of the previous lecture as it is the continuing part of the chemistry of the hydrocarbon in the petroleum. So we should revise the paraffins and the olefins chemistry. What is the objective and the learning outcome of this lecture? Aromatic hydrocarbons in the petroleum. Criteria of the aromatic hydrocarbons, or we can say aromaticity. Physical properties of the aromatic hydrocarbons. Then we have the reactivity of the aromatic compounds. The naphthenes, that is cycloalkanes properties, naphthalene properties, a small exercise after completing the topic, references, and SELO, that is student effective learning outcome. What is the objective and the learning outcome of this lecture? As we all know, the petroleum products are those materials derived from the fossil fuel crude oil or the petroleum, and it is processed out in the refineries. The majority of the petroleum covered to many of the petroleum products includes several classes of the fuels. The students will know the fundamental of the crude oil hydrocarbons and the chemistry of the hydrocarbons, then go for the refining process of the petroleum to achieve the variety of the petroleum products. So the main outcome is to learn the fundamentals of the crude oil, their composition, their hydrocarbon, even the chemistry of the hydrocarbons, how they react, what are its important properties. In the previous lecture, we have discussed about the hydrocarbons in the crude oils. The carbon and the hydrogen compounds are called the hydrocarbons, and in the crude oil, the different kind of the hydrocarbons they exist in, like paraffins, alkanes, olefins, alkenes, unsaturated hydrocarbons, aromatic hydrocarbons, cycloalkanes, naphthalene, naphthalenes, aromatic hydrocarbons. We have also discussed the chemistry of the paraffins and the olefins. As paraffins is having the little affinity towards the reagents, and olefins are more reactive than the paraffins. They show the electrophilic addition reactions. Aromatic hydrocarbons, which were originally named because of their fragrant properties. Aroma means fragrance. We can say the benzene and its first derivatives, which had the pleasant aroma, they were called the aromatic compounds. So the name is given because of their pleasant fragrance. The aromatic hydrocarbons are the unsaturated hydrocarbons having the ring structure and exhibiting the special properties, including the unusual stability, and this is because of their aromaticity. So aromatic compounds always obey the aromaticity, that is Huckel rule, They are often represented as the resonance structures containing the single and the double bonds. However, the bonding is stronger than expected for the conjugated structure. Yeah, it is having the similar conjugation of the single and the double bonds, but it is having more stability than a simple conjugated compounds. It is more accurately can be determined as a delocalized electron density, which was shared between all the atoms in the ring. And this is the important characteristic of the aromatic hydrocarbon, which make its special hydrocarbon in the crude oil. This is the ring structure of the benzene, and you can see here this is the calculus structure of the benzene. 80% of the stable structure contributed by the calculus, and there is the delocalization of the pi electron over the ring, and this is the resonance hybrid structure of the benzene. So the actual structure is lying between these two structures. Actually, the whole benzene structures are the 5 structures, 3 are of Devas and 2 are of Kekule. So here 80% that contribution of the structure of the benzene, which gives the actual hybrid of the benzene structure, and 20% is of the contribution of the Deva structure. So here we have represented the more contributed structure, that is of the Kekule, and this is the, we can say, the hybrid or the resonating structure of the benzene. So in this structure you can see the ring carbon atoms, the sidewise overlapping of the p orbitals, which is forming the pi bond, and the pi bond is delocalizing over the ring. So in the first structure you can see here is showing the double bond, that is a pi bond to this carbon, and here also having the double bond, and we all know the pi bond is formed by the sidewise overlapping of the orbital, and when the internuclear axis overlapping is done, we have the sigma bond. So the pi bond is forming this carbon atom here and here. So here you can see in the one structure, and this can be delocalized like this. So in between, in the another structure, we have the different carbon atoms that go for overlapping and form the pi bond. In the third structure, that is also it over to whole delocalization is taking place in the ring. So the actual hybrid of the structure is lying in between that. Understood? That is only the resonance. What is the criteria of being aromatic hydrocarbons? The first criteria is the structure must be cyclic and contain some number of the conjugated bonds. Conjugated bonds means alternate single and double bond. Each atom in the ring must have an unhybridized p orbital. The unhybridized p orbital in the ring must overlap to form a continuous ring of the parallel orbitals you have seen in the benzene. This is usually achieved through a planar arrangement, or we can say the flat arrangement, allowing for the most efficient overlap. Delocalization of the pi electrons over the ring must result in lowering the electronic energy. So when the delocalization over the ring causes in the aromatic hydrocarbon, it may result in the lowering of the electronic energy. And the last criteria is follow the Huckel rule, that is 4n plus 2 rules. That is, n can be the positive integer here, that can be 0, 1, 2, 3 and so on. Okay, so n always a positive integer and it gives the number of the pi electrons. So if it exhibit this Huckel rule and having the pi electrons according to this 4n plus 2, it is the aromatic hydrocarbon. So likewise, if I put here 0, so what comes? It comes 2. So it comes 2 pi electron. Okay. If I put the n is equals to 0, what will be the number? The number is 2. 2 pi electron. If I put n is equals to 1, then it is 6. So likewise, it comes 2 pi electron, 6 pi electron. Then we are having 10 pi electrons. If I put the value n is equals to 2. So the number of the pi electron will be the 2, 6, 10. That is the aromatic hydrocarbon. If it comes 1, 3, 4, 5. So they are the aromatic hydrocarbon? No, we can't say that they are the aromatic hydrocarbon. So these are the criteria of being an aromatic hydrocarbon. So let's see the physical properties of the aromatic hydrocarbons. As we say, the alkyl benzenes are all the colorless liquids with the characteristic odor. They are lighter than the water. Non-polar hydrocarbons are non-polar compounds. So they are miscible with the non-polar solvents. Always like dissolves in like and unlike dissolves in unlike. So non-polar dissolve in the non-polar solvents like petroleum ether, carbon tetrachloride. The melting point and the boiling point shows the usual regular gradation, means they are having the regular melting point and the boiling point. The inflammable and burns with a sooty flame. This is the important characteristic of the aromatic hydrocarbon and it is tested by this characteristic. So if we want to differentiate the aromatic from the aliphatic hydrocarbons, we always have this characteristic to use. We just burn in the flame, that is the flame test, and the aromatic compounds burns with the sooty flame, but aliphatic compounds they burns with a yellow flame. Now let's see the reactivity of the aromatic hydrocarbons, or we can say the chemical property of the aromatic hydrocarbon. The double bonds in the aromatic compound are less likely to participate in the addition reaction than those of the alkenes. As we have seen, the alkenes are also having the double bond and they generally go with the electrophilic addition reaction. And the presence of the double bond in the ring or the aromatic hydrocarbons do not undergo the addition reaction. Instead of that, the cyclic aromatic compounds undergo the electrophilic substitution reactions. So the most common reaction which is found in the aromatic hydrocarbon, that is electrophilic substitution reactions. The reactions in which the ring act as a nucleophile. You all know what is a nucleophile. Nucleophile is the electron rich species and electrophile is the electron deficient species. So electron loving, that is electrophile, and nucleophile, that is nucleus loving. So when the benzene participates in such of the substitution reaction, the product retains the stability associated with the aromatic electron system, and this stability is lost in the electrophilic addition because of the product is not aromatic. So in substitution, its stability is not lost, but in addition, the stability is lost. That's why they go for participating in the substitution reactions. So the electrophilic substitution reaction, how it takes place in the aromatic hydrocarbon, the benzene is acting as a nucleophile here, okay, and the electrophile is representing the E plus, that is electron deficient species. So this how the displacement of the H ions from the ring, okay, the H ion is displaced by the electrophile, and electrophile goes on attaching to the ring, and this is the product which is formed. So the electron rich benzene makes a bond with the electron deficient species, which takes place in place of the hydrogen atom in the original structure. The reaction preserves the pi system of the electron, or its stability remains. In the addition, it does not. That's why it is more preferable, the substitution reaction shown by the aromatic hydrocarbons. So many of the electrophilic substitution reactions are there for the aromatic hydrocarbons. So let's see, the first electrophilic substitution reaction is halogenation, where the electrophile is chloride ion and the bromide ion. So it undergoes the halogenation with the chlorine or the bromine, and in the presence of the catalyst ferric chloride, so we have the chlorobenzene, bromobenzene, hydrogen is replaced HCl. The nitration is also one of the important electrophilic substitution of the aromatic hydrocarbon. In undergo the nitration in the presence of the sulfuric acid and the nitric acid. So we have the nitrobenzene. It is acting, the electrophile is NO2 plus. So hydrogen is replaced to form the water. Sulfonation. In the presence of the sulfuric acid and sulfur dioxide, it goes for benzene sulfonic acid, SO3H. Okay. So that is the benzene sulfonic acid, SO3H, is the electrophile. The Friedel-Crafts alkylation reaction, even acylation reactions. So alkylations, we are having the alkyl group in the presence of the aluminium chloride as the catalyst. We have the arene, and here it formed the aryl ketone. Here the electrophile is RCO plus, and here the alkyl R plus. So it goes for R, and here RCO. Okay, that forms the ketone group, and hydrogen is removed. In both we have HCl. So these are the important electrophilic substitution reactions of the aromatic hydrocarbons. So the next important hydrocarbon is the naphthene, and these are the saturated hydrocarbons, cyclic. The boiling point and the densities of the naphthalene are higher than those of the alkanes and having the same number of carbon atoms. Usually in the crude oil, the naphthalene of the 5 and 6 carbon atoms are present and having the alkyl substituents. Okay, so alkyl substituents attached to the cyclic saturated hydrocarbons, such kind of the naphthalenes are present in the crude oil. Multi-ring naphthenes are present in the heavier parts of the crude oil. So here we can see the examples of the alkyl substituents, naphthalene. We have alkyl cyclopentanes, hexanes, alkyl cyclo. So this is also the alkyl group, alkyl substituents of the cyclic saturated hydrocarbon. We have the bicycloalkanes. Okay, so in the heavier crude oil, we have the multi-ring cycloalkenes. So this is the methyl cyclopentane, 1,2-dimethyl cyclopentane, 1-ethyl, 2-methyl cyclopentane. So these all are the alkyl substituents of the cyclic saturated hydrocarbons. The another hydrocarbon, that is the naphthalene, having two benzene rings. Let's see its physical properties. It is a colorless crystalline solid. It melts at 82 degrees centigrade. It is insoluble in water and it has mouth ball-like odor. That's why we use it in the domestic applications. The chemical properties of the naphthalene is similar with the aromatic hydrocarbons, as it shows the electrophilic aromatic substitution reactions. But if we compare both the benzene and the naphthalene, naphthalene reacts more easily and readily than the benzene. As if we see the chlorination and the bromination substitution reaction of the naphthalene, it readily proceeds without a catalyst, as the benzene go with the substitution reaction with the presence of the catalyst to give out the product 1-chloronaphthalene and 1-bromonaphthalene. Whereas both benzene and naphthalene can be alkylated using the Friedel-Crafts reaction, the naphthalene can also be easily alkylated by the reaction with the olefins or the alkenes or the alcohols using sulfuric acid or the phosphoric acid. So the naphthalene can easily undergo the alkylation with the alkenes and the alcohols also. So we can see if we go for the comparison, so naphthalene reacts more easily and readily than the benzene. Now we see the reduction and the oxidation reactions of the naphthalene. So with the alkali metals, naphthalene forms a dark blue-green radical. That is the anion salt such as sodium naphthalenide. So here is the sodium naphthalenide, and these salts are acting as the strong reducing agents. So we can see with the alkali metals, these salts are formed which can act as the strong reducing agent. Naphthalene can undergo the hydrogenation reactions under high pressure in the presence of the metal catalyst to form tetrahydronaphthalene, that is C10H12, which is also known as tetralin. Okay, and the hydrogenation also yields the decahydronaphthalene or decalin, that is C10H18. So we have the alkali metals. It form the anion salt which act as a strong reducing agents, and it undergo the hydrogenation which forms the tetralin and decalin in the presence of the metal catalyst. And the oxidation reaction can also be seen, oxidation with the oxygen in the presence of the catalyst transition element vanadium pentoxide as a catalyst to give phthalic anhydride. So here you can see the oxidation reaction of the naphthalene to form phthalic anhydride, and this reaction is the basis of the main use of the naphthalene. So the oxidation is the main use of the naphthalene. So it readily oxidizes. So we can see it is highly reactive than the benzene, that is the aromatic hydrocarbon, and this is present in the crude oil. So here is the small exercise for you all. As you have learned the aromatic hydrocarbons, the criteria, the reactivity, and the naphthalene and naphthalene properties. So do the questions. These are the references for this topic. The student effective learning outcome of this topic, the application of the concept of the topic, which is required for the refining process of the crude oil, and the adaptive thinking skills to understand all about the chemistry of the hydrocarbons. So these are the two important learning outcomes of this lecture. This is all about this chemistry of the hydrocarbon. We will meet in the next lecture. Till then, thank you and take care.